what I'm thinking is this. We finished chapter 29, yeah?
Yeah.
And we do at least like two questions from each chapter, yeah?
Yeah. Okay.
Because Dr. Najib is gonna give us like, I think from 27, maybe one chapter because he didn't like it, like he didn't teach us properly yet.
Yeah. Which
28, he's gonna give us like two maybe or three.
yeah. Then we'll do 29, right?
No, just continue from here.
Wanna continue from here?
No, the last video. I mean, the 28, you see this chapter 28? At 44 minutes, he started 29. Or do you think he will explain it in the beginning again?
Yeah, actually he will. So we'll just start from here. Can you see what? Can you hear what he's saying?
No, I don't hear.
Okay, wait. Where is it? Yeah.
Networks we can just solve resistance and capacity difference. Okay. So today I will just go through chapter 29. And I will try to solve as many problems as possible from this chapter. And hopefully I will upload a couple more problems of my so that I know at the end of the semester you will be pretty much busy with all the courses, all the exams and stuff like that. So you will not get time to go through the questions. And also the questions I'm solving. I'll try to accommodate as many as problems in the classroom. I solve every and hopefully I'll also give some homework. And I'll post a solution right. So I will give additional questions. So we were discussing the magnetic field current, right? This was this chapter. Magnetic field, we were looking for a source of magnetic field, and the magnetic field is like a carrying wire mostly. And from this chapter, there are two things very, very important. One is the ambient flow, and another is Gauss law, right? So ambient flow is like Gauss law, right? You have several. Maybe even if you have one wire carrying line, right? Let's say I take several because you need to know how you have more than one wire. How to calculate. I have wires which are something like infinite length. Okay. Ampere's law, you need to have some kind of symmetry. Same as Gauss. We discussed this. And you just do an ambient loop, we call them. It's like similar to the Gaussian surface. Instead, the surface is an ambient loop. And we will be talking about the length of it. And you know, when you have the current, this axis, the magnetic field will be current. So, for example, you can take any direction for the ambient loop. Maybe you take the magnetic field in this direction for this case. You will take the otherwise. Okay, it's fine. And if you have magnetic field this way, I'm just taking the my length element dl is also the same direction. And what is this case? V dot dl is equal to mu 0 into whatever the current going to the loop, right? And we always say whatever is coming out is going into the surface. It's going into the surface because these are opposite. And this is we take positive, and this take as negative. If you are choosing the direction of the field in this way. If you are taking opposite, you can take opposite. But just learn one way, okay? So that you don't make mistakes. So your current is going this way, so it will be the magnetic field. And you can just solve any problem which is having symmetry. If you don't have symmetry, you cannot use the ambient, you cannot use the Gauss. So we solved one of the example where we had infinitely long wire carrying current, right? And we just draw. We were asked to find the magnetic field at a point here, maybe the word P or I think I didn't mention that P or something, but you have some point here around the wire, and you have to find magnetic field. You have to find magnetic field around the wires. It's the same. And you just draw an ambient loop like this, right? You have the small element going this way. This way. This is the same, right? And you just do V dot dl mu 0 I e. What is the I e in this case? You have I2 coming out of the plane. So you take as a positive, right? And I1.
Yeah.
After you finish this,
I2 was going to
after you finish this, I mean, stop it. I just want to read.
Okay.
This,
After he finishes, yeah.
yeah, after you finish this quickly.
That's how the direction should be decided.
Okay.
And this like
Go back a bit. Let me just. So what he means in
I2
this?
coming out of the plane. So you take as a positive.
He's saying like whatever current enters, if they leave, then they will get subtracted.
Oh. So
Like
what's
say
in them? Yeah, okay.
I1 is entering, but I2 and I3 are leaving. So then it will get subtracted. So that's why it's look I2 minus I1 minus I3. Look.
Yeah, right.
That's how the direction should be decided. And this case you have only one I, so the I thing will be area. I what will be the unit? You have the ambiguous unit like this. The vector B and DL are parallel, right? So you have every border will your B will be like this, and your here will be B. So it should be, and it is uniform. So you take B outside and mu 0 I. And what is this DL length? Don't get mistaken with the area or something. In the magnetic field, we always talk about the length. Okay, so that's why I use the potential L. So what is the length of this loop? 2 pi, right? So should be mu 0 I over 2 pi. Okay, now we will go to the other laws. We will come back to the ambient law later with some complicated questions. But let's see how the Weber-Sauer law looks like. So the Weber-Sauer law. When you have any kind of wire, then you have to have, if the wire has to be infinite, you can apply the ambiguous loop and just solve using the ambiguous loop. But when you have any kind of wire or any other structure which doesn't have any symmetry, then, for example, you have some wires like this, catenary wire, right? And you want to find what is the magnetic field around this. It's a point B or P or whatever. Since I put P, let's say P. And what you have to do, to take a small element, DL, okay, and see how the DL is having small magnetic field at this point. Let's say this is at any center. Okay? And now it says the small magnetic field should be equal to mu 0 I, the current, whatever it is carrying, over 4 pi, B across R cap over R square. Okay? The important thing about this law is that this is the first time we are seeing something like this. You have a vector cross to a unit vector. Right? I'm not taking the cross product with this vector, but say R cap is just a direction of that, the vector R. What is D across R cap? What is it basically? You have a cross product, right?
He's writing too fast.
Right? In most of the cases,
Will you go back?
I stopped until where? PDL and he's using the same equation, yeah? B
Yeah.
times DL.
Yes, yes.
Wait, let me just write it down.
Yeah.
B dot DL is equal to mu 0 I n. Okay. If I took B to the other side, it became pi DL. Are you also writing that?
Yeah, I'm also right.
Did you finish writing?
No, still writing.
2 pi R.
Yeah, finished.
Okay, I'm just starting this part here.
Yeah.
Buyout. What's the buyout, bro? This one?
It's the name of a person.
No, I mean the law. What does it? Do we also like read it so much? Yeah?
No, he's just saying like, say for example, you have a wire and at a distance P, this formula you can use to find the magnetic field at the point P from the distance. Or
Oh.
yeah.
You can find the formula like by that distance.
Yeah, by the formula given, yeah, U naught I by 4 pi dl into R by R square. With that formula you can find the magnetic field at a point P.
Which one? What did you say again? The formula what?
The
D what?
dB.
dB is equal to mu I.
Yeah, that one.
Mu I 4 pi. This one.
Yeah, that one.
Hmm. Bro, by the way, when are you gonna come to uni tomorrow? What time?
Tomorrow I'll reach by, if I take the 9 o'clock bus, 10
You want
o'clock.
to revise also on uni? Like
Yeah, I
last
don't think
minute
I'll have time to revise on uni because like by the time I reach, it'll already be like 10:30 or 10 o'clock.
Oh shit.
Yeah, because I come by bus, I don't come by car.
Oh yeah. But don't
How do you?
don't you have license?
No, I used to come by car, but then my my dad gave the car to the garage, so now I cannot come in car.
Oh, since when?
Then there was a small crash, so then I had to go to the garage.
Oh, what happened?
Like I was at the signal, and then like I was driving, and then the red signal came out of nowhere, so like I had to stop here.
Yeah.
I put like a sudden brake, so then the person behind me came and just crashed into me.
Hope
Yeah.
you're doing well.
Like, what?
It's okay. How long was it?
It was like 1 month back, but like the what is it called? Like my car didn't have much damage in it, so we thought, okay, we could do it like a bit later. You know what I mean? Yeah, because like we had some uses because we had to go here and there, so we needed the car. So we were like, okay, we'll give it after 1 month. So my dad just gave it like 2 weeks before.
This is good.
Yeah.
Okay. It's okay. Everything, inshallah, is well. Everything will be okay. Okay. Yalla, let's continue.
Lovely.
This R here, this is a unit vector. Okay? This shows the direction of that. Most of the cases, the magnitude of this one will be 1. Right? When you have a unit vector, it's having, for example, I cap, magnitude of I cap is 1, magnitude of J cap is 1, right? Or K cap is 1. Like R cap is having the magnitude 1, okay? In most of the cases. Let's see how we can solve the same problem. Bayes-Sauber law you can apply anywhere. It doesn't need any symmetry. If it is a symmetry, it doesn't care. Okay? But ambiguous law, you need to have particular symmetry. Let's see solve this problem by using the Bayes-Sauber law and see how we get the same result by integrating this. It's more like the problem whatever we have solved is for find the electric field. So I'll write the problem again. Example this one, right? And infinitely long in while. Okay, so one point, there is an widely, and a distance of x from the line. So you have, in most of the problems, I will give you the schematic, especially when it comes to the magnetic field, but this kind of problems, you already know the schematic. You solve this, find the electric field, you have infinitely long wire, right? And you have to find the electric field at some point P, right? So you have the long wire. This is infinitely long wire, right? And then you have some point x from this wire. Okay? And you have to find it. And this is carrying current I, by the way. This is carrying current I. And you have to find this is carrying current I to have a magnetic field around this wire. And you have to find the magnetic field at a point, something called P1. If I mention that at a point P. If you just assume that as a point, okay? Now, if this is if you are using the ambient limitation using this loop, right? You don't need specifically use the Bayes-Sauber law or ambient loop for any of the problem, unless I specifically mention solve using the Bayes-Sauber. And I don't want to make your life difficult. This kind of problem I will not be asking to solve using the Bayes-Sauber. But by solving this, we will learn something to solve the different kind of problems. Okay? So the reason I'm choosing the same problem to make you understand that this is much easier than what we are solving. And also, you can have
Are we given the value of
mu0 value I will be giving. I will be given. If I'm asking a numerical question, I will be giving you epsilon 0, mu0, and any other constants. Okay? Pi already you know. 3.14, 1.92. We can just keep going on. So, how we solve this? So we are talking about the small element here, right? So we have to find the small element.
Small element.
Okay. This is my idea. Okay. I want to find the magnetic field created used by this small element at point P. So I just take this point. Okay. And I assume that, since this is correct, I assume that this is at a distance of y and this is at a distance of x. And I just see that my vector to the point is that. Okay. And I can apply the Bayes-Sauber law, which is small magnetic field created by this dl point will be mu0 I over 4 pi dl cross r cap over r square. Right? And if I want to find the total magnetic field, each of the small element on this infinitely long wire, so I just do integral of b from word to word.
Okay, bro, so stop.
So I'm taking this as a point 0,
Yeah.
right?
Stop. Okay. So here he just used the same equation before doing anything. He put first dB. Because it's first, we know that this question is what? Chapter 29, yeah?
Yeah.
Why? Because it asked infinity long wire and what? infinite long wire, find B at a distance Px from the wire.
Yeah.
So first we have to find our element.
Yeah.
Okay, point. This point is like what the how it becomes a triangle. Like how we get the three adjacent hypotenuse like this.
What are you talking about? Which one?
I'm saying like he finds his element, then he
Yeah.
puts the equation that's always like the same.
Yeah,
This
yeah,
is
yeah.
what MOI over 4 pi
Yeah, right. So what?
4 pi 4 pi dlxr over
Mm-hmm.
r square.
Yeah.
Okay. And
Okay.
then why does he make it b equal integration?
Why does he make what?
CB is equal to integration b.
Where does it say that?
On your right, you don't see it?
Integration B? Oh no, he's wrong. He's gonna change it. He's gonna put delta B. dB.
Oh.
Look, watch. He put dB. That's it.
Oh yeah, I see it. Yeah. You're right. Okay, continue.
Right?
Go
So
back.
you are taking
Go back before he made the GB. Maybe he
Yeah.
said something.
0 in the result. From what to that. So I'm taking this as a 1 0, right? So if that is the case, it's an empty infinity. It should be positive. Okay? Now, what is dl cross r? Is this? Sorry, this is d. So this is d. This is integral of whatever this one. Okay? Now, what is dl cross b? Dl cross r cap? dl is in this direction, right? The length element is in this direction, right? This is a vector element. The length element is going this direction, and your r cap direction is going this direction, right? So you are taking the angle between. When you talk about the dl cross r, you are talking about the dl r sine theta, right? And this theta is the angle between. Okay? Or you can also do like this.
Oh, bro, he used the
This you can
same
take
equation again.
pi minus theta.
Hmm?
He
And what is
used
sine?
DLXR and DL going and R going. Sine. It's the same one also. DLXR.
Yeah. Cross product.
Mm-hmm.
Yeah.
Okay.
Uh,
So these are the
theta.
equations.
Yes.
Sine pi minus theta. Should be sine theta.
Okay, stop.
So now,
Yeah.
Yeah, here, let me just write this. Okay, so DLXR, this guy,
Not X, cross product.
yeah, DLXR, which is cross product,
Yeah.
will become DL, this, and then R will become this, and then it will be equal to, not equal, yeah, it will be sine theta. Sine theta.
Hmm. Yeah.
Okay.
Okay.
And then the other one is just the next to it. Sine
Yeah.
pi minus 0 or pi minus theta?
Pi minus, wait, which one? Sine pi minus theta.
Sine pi minus theta, which is equal to sine theta. Okay.
Yeah.
Okay.
Okay.
Mm.
Alright.
and what is dl by the way? You have a small element on y-axis, right? And I can call them like we did for the case of the electric field. We can call them as, since it is on y-axis, I can call this small element as dy. You can use any axis. The problem I solved for my convenience, I use this as a y-axis, and that was an x-axis. But if I am giving that solution, you will see a different kind of notations. But it doesn't matter what kind of notation you use. It's just a convenience. If as far as this distance is x, in your expression, the final expression, you have to express the normal field in terms of whatever this distance. Whatever the other axis or whatever the length or element or whatever you use, it doesn't make any difference. Okay. Now, so this is real cross r sin theta, right? So I can write this one dy, right? The magnitude of the small element I choose as y-axis. So I have dy. And what is r cap magnitude? This one, right? It's just a unit vector direction. It just show you a direction. When you take the magnitude of that direction, it's just one, right? And this can be written. So since it is, this is dy and this is 1 and this is whatever it is. Okay? So you have real cross. So let's just write dv. Mu0 I over 4 pi and dl cross dy sine theta over. Okay. Now we can solve this one. I have solved before for the electric field. Use the same thing. How you solve this one?
This is still not solved.
You just
No,
substitute
you solve it. Bro.
whatever the dB value there, right? And you have to make substitution for R. What is R basically?
Associated D,
R is
I'll send you a photo of
square
it.
of x square plus
Huh?
y
I
square.
have
And
a
what is sine
third
theta?
version of this. I'll send you the photo. What's that?
You have what solved? Or what?
I have like a simplified version of that. I'll send it to you.
A PDFied version?
Simplified version.
Simplified. Huh?
Yeah. Why do you put so many question marks?
So you can get it. Like it will be on your top messages.
Oh my god.
Maybe you're a businessman. You don't see this.
Yeah, too busy. Yeah, what's
So what the hell did he do?
just try reading it by yourself, you'll understand. Just take a minute to read it.
Oh, I don't understand shit in this. Infinity is equal to tan infinity. Theta is equal to tan t infinity.
Yeah.
Y is equal to x tan theta. Sine is equal to mu I. Okay, we're at now mu I and 4 theta, right?
Yes.
And
Look,
our
you got it.
second one is dy sine theta r squared. What happened
Yeah,
to that? It just disappeared.
Which one?
Can you share your screen on the photo and point at it? Explain to me.
Yeah.
Because
Can you look?
yeah.
Yeah, which one? Which one?
Where we stopped in the after Najib, he stopped at dB is equal to mu I over 4 pi, then dy sine theta over r squared. This is where Najib stopped.
Okay, where do you have a doubt?
The whole thing, is it like related to the same question or different?
Yeah, you understand till this?
I understand until where Najib stopped at dB.
Yeah, okay, that is this. He stopped over here. This
Where?
one.
Point to your mouse, I can't see your mouse.
Yeah, this one. 1 sec. Yeah, this one.
This is where he just simplified dB, you mean?
Yeah. Look what he did. He took uh y. Yeah, he took y as x tan theta. And then he derived dy and by d theta to get x sec square theta. And then he substituted that over here. Look, substituted that over here. That's where he got this. Get it?
When he pulled that up.
Yeah, then he pulled the x square out. Then he got 1 plus tan square theta. And then 1 plus tan square theta is equal to sec square theta. So then he got that. So then he cut the sec square cancel, c cube, and then c cube
No,
is
but
remain.
I'm still at this part. Okay, this is I think is easy, but this part above it. You see where Najib stopped?
You want me to go to the this thing?
Yeah, because this is where I stopped. Like, see where Najib stopped until here. Yeah, I'm at here. This is where I'm. MOI 4 pi dy sin theta over r squared.
Yeah, okay. Just keep watching this.
If your y minus theta is also x theta, so it should be x over x squared plus y squared squared. So you have everything here, right? Mu 0 I over 4 pi dy, right? X over square root of x squared plus y squared. I'm writing like this now. And over r squared you have. Maybe I'll decide.
Bro, it's sine. Wait, I'm stuck at this. It's
Square of the
sine.
square root.
Yes, stop here.
Square of the square root will be
Yeah.
It's sine theta because it's like opposite
Cross
over hypotenuse.
Because it's a cross product.
Yeah, opposite over hypotenuse or no?
Yeah, yeah, correct.
Because sine is OH, right?
Yes, you're right. Opposite one.
So the opposite is, the opposite is x, and the hypotenuse is the square root x squared plus y squared. Okay, and then here what?
Yes,
After
correct.
this, what did he do?
Yeah, watch.
Same, right?
This is what I showed you here. Look.
Oh. Yeah, and then he turned the r squared into this,
Yeah,
into x squared plus y squared.
yeah. Sorry, sorry.
And the square root is basically 3 over 2.
Yeah.
And then what about the dy sign on the thing
Huh?
with dy
What?
sign above it? Well, go back to Najib.
This one?
He rewrote it as dyx.
Yeah.
Wait, I'm stuck here. Well, okay. Okay, so basically after this, db for oi, this guy mu I, di sine, and then mu I, dy minus x. Okay, why did he
Yeah.
turn sine theta to minus x?
Huh? What?
Bro, why did he turn the sine theta into minus x?
Sine theta. Where is he? Where did he do that? No. He turned sine theta into x divided by x square plus y square.
What? From where?
Look, x divided by x square plus y square.
How did sine theta become x?
Because look at this. You see this?
Yeah, x over square root x squared plus y. So he replaced it there. So
Yeah.
okay, so it became mu oi over 4 pi, yeah?
Yeah.
And then what's r squared? R squared we said is square root x squared plus y squared, yeah?
Yeah.
So when you write it down, if you just write the r, it will be what? It will be x squared plus y squared, and then both of them are like square root, yeah? Square root
Yeah.
is what? Is
It's
1
the
over
same.
2. But plus,
Yeah.
but power of 2, it will happen what?
It'll become x square plus y square.
No, I mean if it's power of 2. Not the whole thing.
Yeah, I
The
know.
bracket
Look.
will become 1 over 2, right?
Yeah, look. That's what he did.
Yeah, 1 over 2.
Yeah.
And
That's what he
then
did.
and then he will write the x over x squared plus y 1 over 2. Isn't r supposed to be... bro, you see the r?
Yeah.
Did he make a mistake here?
What mistake?
Point your mouse to the left, the middle left.
Yeah.
So you see after 4 pi,
Yeah.
the left side. This one, not left one. You see right. Yeah, here. You see 4 pi. After this, after the 4 pi is the r squared, right?
Yeah.
Isn't it supposed to be x squared plus y squared 1 over 2?
No, it's not because it's r square. If it was r, only r, then it would become 1 by 2. But since because it is square, you multiply the powers. So what is 1 by 2 into 2? 1, right?
Hmm.
So the power is 1.
Hmm. And then 2 times. But but the powers were originally also x squared plus y squared, isn't it?
No, originally the formula for r is x square plus y square to the power 1 by 2. So if you square it, that will become x square plus y square to the power 1. That's what he did here.
So if we didn't, if the r squared wasn't r squared, the x and y would have been just x and plus y
Yeah, correct.
without their powers.
Yeah. No, with the power, with 1 by 2.
No, I mean both of them will be like power of 1, power of 1.
X square plus y square, you mean?
Yeah, x squared plus y squared.
Yeah.
Because in the graph he said r is equal to what? Is equal to square root x squared plus y squared. I thought that's...
Yeah.
Well, I'm just saying yeah. Or you understand what I mean?
I get what you're saying. You're saying like if it was not squared, then it would be 1 by 2. Yeah, you're right.
Okay, we'll just write it this way then.
Yeah.
Okay, and then dy, it's the same, yeah? But then we change the sine theta into what?
Sin
To
theta
x
is
over
x over
x
x square
squared
plus
plus y, power of 1 over 2, which is just the square root.
yeah.
And then
Okay,
we
got
just...
it.
Yeah, okay, understand until here. Okay, and then
Good,
what?
good. Yeah, and then just watch what he's doing.
X dy over x squared plus y squared over
dy over
3 by,
four.
right? Now you have to find,
Okay, he added them together.
Yeah, yeah.
b
But he cancelled 1x?
minus infinity
Or
plus
what?
infinity
What?
into 0 I
Why
Oh,
did he
no, he did
cancel?
not
What
cancel
did he
anything.
cancel?
Okay, okay.
x
He didn't cancel anything.
Yeah, yeah.
dy over x square plus y square 3. Okay. So there are several ways to solve this one. We will use the same technique as we used for the case of the electric field. We use the substitution method. What kind of substitution we use? We use trigonometric substitution, right? I hope you are familiar with this. So simply you take the sides, right? You have y, x, and let's say r, and you have theta here, right? So you define tan theta equal to y over x, and you differentiate both sides. So this will be 1 over cos square theta d theta should be dy over x, right? So dy you can write in terms of this one, x over cos square theta into d theta, right? Yeah, so when you do this trigonometric substitution, you are trying to change this all the values into a trigonometric form. So whatever that x square plus y square over 3 by 2 you have to change to a trigonometric form, right? So what is cos theta here? From this or from that one? The cos theta will be, or cosine theta will be x over r, right? What is r basically? X over x square plus y square half, right? And most of you got confusion with this one. Just remember that if you cube this function,
Bro, what the fuck?
okay?
Bro,
So
Yeah.
you have this one there,
stop here.
Yeah.
right? So you can write
You see cosine? X over
That's why
r.
I said. That's why I said. Look at mine. It's much simpler.
Yeah, I'm just saying cosine. Bro, he said sine, yeah? Sine theta is what is x over x squared plus y squared, yeah?
Yeah.
The square root of x squared plus y squared. Sine is what is opposite over
Don't look at this.
hypotenuse, right?
Don't look at this. Just
I'm
look at
just
mine.
saying-
Just follow that.
No, I'm just saying this is like generally. Sine is what? Opposite over hypotenuse, right?
Yeah.
And cosine is what? Adjacent over hypotenuse, right?
Yeah.
Then what do you write on cosine? X over r. Is x the adjacent here?
Yeah. Of course it is.
Adjacent means down,
Yeah.
and the opposite,
Opposite is y.
and the hypotenuse.
R. What is opposite to theta? Y, right? What is adjacent to theta? X. Simple.
Yeah, but why in the left one? He said the opposite. I mean not opposite. Sine is what opposite, right?
Yeah.
What's the? Oh yeah, because the theta was up.
Yeah.
No, you see the theta of the original question. I mean, go back to like what's it called?
Yeah.
Go back to 19. Yeah, this one. You see,
Yeah.
his theta's there. Is up. I mean,
Yeah. Correct.
so the opposite is like under.
Yeah. You're right.
And the adjacent, I mean, our hypotenuse is r, which is x squared plus y squared. Yeah, bro, but he made it look like the cosine and sine they're similar because just the theta is different from the side.
Yeah.
Okay,
That's-
yalla, just go back to this one.
Yeah.
I have to write all of these substitute trigonometrics.
Yeah. It's important. Write it down.
Yeah, I'm writing it. Okay. Okay, so what is he trying to tell us in this thing here?
He's trying to solve the integral
Hmm.
because that's the only way you can solve it.
Tan is tan.
half, right? And most of you got confusion with this one. Just remember that if you cube this function, you will get this one. Okay? So you have this one there, right? So you can write x squared plus y squared 3 by 2 is equal to x cube over cosine cube. So everything is now in terms of theta function or the trigonometric function. That's the idea of substitution using trigonometry. Because you don't know what is the infinity of some value, right? If you want to integrate. So you use the convenient method. Now, if I just put everything here, this equation will become, right? And what are the limits? Just check that. So when you substitute these things, when your y goes to infinity, right? For example, if your y go to infinity, your theta will go to pi by 2. And y go to negative infinity, it will be minus pi by 2. So your limits also changes.
Bro, let's just do the cases that he does, not when he explains every single possible question.
What?
I mean, I know I'm saying If we'll like do questions, we'll just use the cases that he showed, not like every single possible way.
Yeah, okay, no problem.
I don't know why he showed everything.
Yeah, it's fine, just ignore it. Use what I said.
Units, y is equal to plus infinity, y is equal to negative infinity, theta equals, this guy equals pi over 2 and pi negative 2.
Yeah.
Okay, I wrote all of these things down. Okay, now what? After we found every cosine and sine.
Yeah, then just what you call? Wait for it to what am I saying?
Wait for it. There is no waiting.
No,
It's not
just
computer loading the
And
answer.
mu 0 I
It's
over
your
4
brain.
pi, and you have x, just leave the x there, and you write dy instead of dy x over cos squared theta into d theta, right? Over, x over cos squared theta d theta, over, I have x cube over cos cube theta. Now I can cancel several of these things. This can be cancelled out. This all things can be cancelled out with this one, right? So I will have minus pi by 2, mu 0 I. You can take outside of the bracket if you want. 4 pi cos theta, right? This will go up to b theta. You have one x remain here, so this will be. Can you check that? Your cos cube theta is 1 over something, right? So when you take this one, it will just, if you want to cancel this one, you just go like that. So this will be remaining like this. Now you can integrate minus pi by 2 to pi by 2 to minus pi by 2, whatever this cos theta into d theta, right? Can I wipe this part out? Right, if you want to take a picture. Now, because I will not be, see, the reason I just choose minus infinity to infinity is that this is very common, and when I change the limit, for example, minus infinity to 0, the question you remember when I asked for the one of the quiz, or from 0 to plus infinity, I can change this in any way. I mean, I can even put this point at here somewhere, and I can just use it. Just remember that this bytes overflow is so convenient to use this. Now, let's see how the result comes for this. Now I'll just go from here. So b will be equal to so mu 0 I over 4 pi, right? Minus pi by 2 cosine theta. What
This is
the
still
integral of
continuation of the question.
Oh, sorry, one x.
Hmm?
What is the integral of
This is still continuation. Yeah?
sine theta? So
Yeah.
this will be mu 0 I over 4 pi x sine theta. What is sine pi by 2? 1, right? So this will be mu 0 I over 4 pi x 1 minus 1. So the result will be, this will be 2. You will cancel with this one. So mu 0 I over 2 pi x. My point is at a distance of x, right? If I ask you a point R, you just replace it. So this is the result. This is minus pi by 2, minus pi by 2. So this will be like this. So this will be 4 pi, okay? This will be 2. So this 2 and this will be cancelled out. So the final result will be mu 0 I over 4 pi, so over 2 pi x. Come on, more clear. Take a picture or write, if you are writing it down, that would be the best. Let's go to the next.
Stop it. Okay, so this is just one question. Okay. Sine theta. You're yawning?
Yeah, tired.
Bro, before we came, I slept like for 30 minutes.
Damn, I didn't sleep.
I tried, bro. I needed that energy boost.
I cannot sleep in the afternoon. I don't know why.
But I can't sleep at night. Or
Yeah, that's good.
put an alarm for 8 a.m. today. Like
8
tomorrow.
a.m.
Yeah, so tomorrow I
Why
wake up
8 a.m.?
early.
Some is at 11.
Yeah, I have time to revise, bro, at least. Yeah.
What time are you gonna reach?
Gonna go to uni like 8:30 maybe.
Where do you live?
Rahmaniya.
What?
Rahmaniya. It's called Rahmaniya.
Where is it? Sharjah?
Yeah, Sharjah. What about you? Also in Sharjah?
I'm in Dubai.
Oh, in Dubai.
Yeah.
There is buses in Dubai that take you to US.
Yeah, the US bus.
The university city, you mean?
No, the university US bus, not the university bus.
Hmm.
Like US provided like different buses for us.
Oh, he changed this into 4 pi. 4 pi 3. 4 pi x. 4 pi x. This became 2. Cancel this guy, cancel this guy. Are you writing this down or you finished?
I'm writing it down. But like, you have to remember that whatever he's doing, it can be like twisted into like a different question. So you have to keep that in mind.
Yeah, but you have to just make it similar, man. Because Najib he likes the same style. Okay, so I just want to go. We just have to go through everything quickly, then we'll do the questions. Yeah, I don't want to stop and like try to understand each part again.
Yeah.
Yeah. Okay. So let's go to next question.
I'll start.
Yeah, start. Go to next question. After that, then after that. Well, let's finish all of them, all of the whole 2 videos.
Now I will have.
And then we'll go through each question again.
Yeah. Okay.
We'll finish all of the questions from this chapter. Then we'll go back to 28. Then go back to 27.
Okay. No, we'll go back to 27 and then we'll go back to 28.
Yeah, sure. No. I mean, we'll have a fresher memory for 28 because yesterday.
Okay, then 28.
No problem. Okay, let's just not waste time.
Alright.
What time is it now?
We'll solve a lot of them. I'm solving everything. When I ask the question for the exam, it's easy for you to understand. Now, I have find the magnet. I have another question. Find the magnetic field created by circular loop of radius carry current I at its center. So you have to find the magnetic field. Circular properties are find magnetic field at its center. So I'll make clear the sentences. Because if I ask, okay, current carries circular by the center, some of you may get confused with the current at the center. So it looks like this. You have a circular loop, okay, and it is carrying some current. So the current is on the wire, the loop, okay, and you want to find the magnetic field at the center. What will be the center? What is the magnetic field at the center?
Going out to
Which direction? You will not do it. So you have the wire. The current is going through the wire. If this is the direction, okay, then the magnetic field will be out of it. If my current direction changes, what happens? It will be no problem. So in this case, I most of the problems of this kind of systems I will be giving you the direction of the current, so that you can decide the direction of the magnetic field. That's specifically asking the direction. Now, the reason I wrote like this is for the flow. Now, how we solve this? How do you solve? One thing is that I will be giving you some question like infinitely long thing. So for sure you know this. There are 2 ways to find this. One is the translation symmetry, another is rotation symmetry. Right? So when you are drawing an ambient loop, you have, for example, a wire of length L. You cannot use the ambient loop, right? Unless you consider this length is infinite. Because when you have the ambient loop like this, right? When you do the translation symmetry, it loses. Right? It still holds rotation symmetry. Similarly, Gauss's law, when you have a infinitely long wire, right? We just assume that there is a Gaussian cylinder, right? But if you move, it's infinite. So you still hold the translation symmetry, and when you rotate, you have the. And for another example, infinitely long sheet. Remember. So when the sheet is infinitely long, right? So you do the translation, you just get the same. So if you do the rotation, you get the same. In most of the questions, when you practice the questions, you get this. But intuition, you will already know that. This kind of things. You can use the Amelian loop for this one, but this one I really wanted to solve using the Beer solver. So all the examples what I'm solving is using the Beer solver. So what will be the this is given previous R, right? What will be the small current created by a small element here? Same figure. For example, I have a DL, right? We did this one for the electric field. Same thing. We just assign theta here and then take the DC, right? Remember? And what is the direction of the R vector in this case? This we are looking at the center. The magnetic vector is this one. So the other vector will be this direction. Right? So what is dl cross R? So what is the frequency number? You have magnitude of dl, right? Magnitude of R into sin. And whenever you look for the dl cross the direction of this R, whenever you change the dl, the R will also go along with this, right? So this theta will always be 90 degrees, which means this one. So this will be dl, and what is the magnitude of the R? 1. So this dl cross R will be just magnitude of dl. And what is the magnitude of dl? You have the radius R, and you have this theta, right? So this is a length element. So you can write this one in terms of R and d. Right? So the small magnitude created by this dl element at the center of mu0 I over 4 pi will be dl cross R here over R square. So mu0 I over 4 pi, right? This will be dl cross R will be dl, it will be R d. So R d theta over capital R square, right? You have the R here is 0 is. So that will be capital, right? Now you can solve. You got the dv. Now you integrate from what to what you have integrated? 0 to 2 pi. You have the circular loop, right? So the maximum can go 2 pi. So the magnetic field will be 0 to 2 pi. E. So this will be mu 0, 0 to 2 pi, mu 0 I over 4 pi, right? R you can cancel R d theta over this, let me write that. So this will be mu 0 I over 4 pi. R, you can take R out, sure, because you are only integrating on the d theta. So what is this is the simplest form. So you have mu 0 I over 4 pi R into 2 pi, right? So this will give you mu 0 I over 2 R. So this is your magnetic field created by the whole loop. Okay? So this is how you apply the Beer solver law for kind of loop problem. We have this one. So now you can have any shape of the wire. So just remember, when I ask you about the Beer solver law, mostly I will be asking the wires in different shapes. Okay, so for that you should know how to define the small element of the magnet, the magnet field, and then you should know how to find the cross product between that small element to the direction of the magnet field. Right. Now, sorry, we will have some questions like Preda mentioned, but we are not talking about the surface or some other shapes, right? So we only talk about the length element, the Amelian loop, the magnetic field created by, even if it is a three-dimensional object, for example, a thick wire, it's a three-dimensional object, right? And in any case, you will be, the magnetic field will be decided by how the current is flowing through the wire. So, unlike the complexity with the electric field, this is pretty much easier. I will be asking questions for sure, three-dimensional elements like, for example, let's do some
three-dimensional elements.
Thick wires.
Yeah.
So you have the thick wires, right? And I'll be asking you to find the magnetic field outside and inside. Right? It's a three-dimensional. Whenever we talk about a thin wire, mostly we consider this as one wire, right? Infinitely thin wires. So let's do a problem. Question. We'll do find the. I think I have some problem. You can see outside like this. But mostly, when you have the field, unlike the electric field, when I ask you about the three-dimensional object, most of the questions will be you can solve by using the Amelian. I'll make sure that there is a symmetry for this, so that it is easier. A thick wire of radius carries
Oh, can you stop here for a second?
Yeah.
Stop this for a second, quickly. Just want to write down the part.
Write down.
2 pi dB 2 pi 0. Just count until 10 and I'm done.
No, take your time.
Good thing we started early.
Yeah.
I still feel like, under understanding. Like I still don't know how to solve anything.
Why do you feel like that?
Because we just didn't do questions, yeah. So that's maybe why.
Oh, no, it's not that deep.
Like I'm gonna go in the exam, just not know how to do anything.
The questions that will mostly come, he said, is from the questions he's taking in class. So it's fine. Like all the questions he's doing in the class, that's what will come for the exam.
Bro, I used to be this type, wallah. Like the what type? Like before, I don't panic until last time because I know when I panic, I do the best. This is not the case anymore. After
You don't
grade.
panic.
Huh?
You're not panicking anymore.
No, it's not that I'm not panicking. I panic and I still fail. I can't do it like how I used to.
Oh my god.
Like under pressure, diamonds are created under pressure. I am broken under pressure.
Yeah, you're the diamond.
It used to be though. Shine bright like a diamond. Okay, continue.
Wanna play?
Yeah. Current, all radius, carries,
Sometimes we use hyphen.
total.
Now I will ask you first one calculate the current density. Okay? And then there's a reason I just ask you first the current density, the magnitude of the current density. Okay? And then I will ask you find the magnetic field. Find the inside and outside.
It's cross sections.
Second, I'll ask you to find inside. Okay? So how do you solve this? What is the current density? You can simply say I over it, or this is that whatever the current pass through a cross sectional area, right? That is why I just specifically mentioned this one. It's passing uniformly through its cross section, right? So you have, let's say the solution. You have, for the first part, you have the thick wires, right? And you have the thick wires are carrying current uniformly, right? So you just assume that you can assume whether it is going in or out. Okay, just make sure that you choose one of the direction. So you have several of these coming out. You don't need to do these doors, but to make you more understanding, you just have a current coming through this cross section. Okay, it's the same. You just
Is it solution or solenoid? What did he write? Or A?
Okay, and the
Huh? What did he write above A? Solution or solenoid or what?
Yeah, solution.
Okay. I thought he was writing some. Bro, did we even start the solenoid or anything part? I don't think we did it until now.
Not yet, he will.
Oh.
Yeah.
Okay, draw the circle.
current density you can define magnitude will be current over the cross section area. And what is the current dimension here? I. And what is the cross section area with radius r for this circular cross section? It's pi r. Right? So the first part is solved. The second part, you see, this is once you understood the question, it's very easy to solve this. The second part, I'm asking you to find the magnetic field outside, right? So be outside. So you have the thick. You have this thick wire, right? You have this, okay? And this is having radius r, okay? You don't need to just this was the reason I just showed this board to show you when it is carrying current, the field is outside. So you have this thick wire. Now, if you want to find the magnetic field outside, you just draw an ambient loop, right? This is having, let's assume that this is having radius. Then you just use the ambient loop. You know the should be equal to mu 0, right? And for the case of outside, this will be the
What's the law called?
you have I can carry this.
Huh?
What?
He said use the ambient law or?
Yeah, Ampere law. Ampere law.
Ampere law, okay.
Right. So what is this? What is the ambient loop like with R? 2 pi r, right? So this will be mu 0 I over 2 pi. This is the case when you have outside or your ambient loop with the radius of r is outside of the y-axis r. Okay. Now when it comes to the inside, it's not 0. It's going to be a little bit tricky. That's the reason I asked you about the current density. So you have this cross section, right? Should be like a fraction. Okay? You are having some current, right? And unless you go to the surface, you are not talking about all the current coming through the ambient, whatever the ambient loop you decide. For example, you have inside. So you have this one. So let's say you have field like this. Okay. Now you want this is having a radius of r. This is having a radius of r. This is having a radius of r. Right? So you want to find what is inside. And you can go all the way from here to up to the surface, right? But it should be below the surface. If you are at the surface, definitely you will have all the currents included in this equation. So this will be B dot dl.
V dot dl mu equal to
Right?
I.
So in this case, let's assume an ambient loop of radius r. Okay? So you have the uniform magnetic field through whatever the region you take. That is mentioned that in any cross section you have the uniform magnetic field. B N U0 I. What is I in here? That is the yeah. So you have the I in should be J into A. What is J basically for the whole current? That's the current density, right? I over what is A? Pi capital R square, right? J we are talking about the whole current density. And what is the area? Whatever we are talking about, this one, the small one, pi small r square. So this will be the current in will be I into r square over capital R square, right? So you can write this one B. What is this one? 2 pi r, right? Right? And then mu0 I r square over capital R square, right? This r square and this r can be cancelled out. So your magnetic field inside will be mu0 I r 2 pi capital R square. Right? Now, if I ask you to plot the magnetic field carrying a thick wire, the current carrying thick wire, magnetic field at different points from the center to anywhere outside, how do you plot it? The graphical plot. Magnetic field, right? I have the surface here, R, and it's going as a function of R, which means I should start the magnetic field from this point.
Oh, can you stop for a
second? And it changes as the magnetic field as something, right? So it is almost linear with this one.
He stopped at like B 2 pi r. He changed he first took the integration of dl, which is L, which is area, and the area is like a circle. So a circle is what, 2 pi r, right?
Yeah.
And then he equaled it to what? To the same one, mu OI, which is after I is IN, right? IN. So IN is what? Is r squared over r squared.
Yeah.
And then he did the same thing, but he just took the thing down, just like Gauss's law originally.
Yeah.
Okay, now he's doing the graph again.
No, he's just doing
Hmm?
it. He's just drawing the graph for it. Like a new graph.
Hmm.
Yeah. Shit.
What? You scared me, dog. What happened?
No, I accidentally closed my tab.
For what?
The island. I have to open it again. It's fine, it's not that deep.
Yeah, it scared me. It's something else.
Yeah. I'll play?
Yeah.
Right inside.
He finished, but I don't know why he's like writing
It's smaller. Then it
his
goes.
graph.
No, I think he's just showing you what to do after that.
And what is the when you have what is the turning point? When you are at surface, this R will be this R, right? Correct. So that point will be the maximum. This is proportional, right? It is proportional. And this is the maximum. So this is a three-dimensional problem. And this is all about the ambient things. Then we will go to a new concept.
100% think you'll bring. This is like I think the easiest one until now.
So far it is clear, right? So now for the ambience law. I can have different kind of shapes. This is just, I gave an infinitely long thick wires, right? I can make the thick wires in different shapes. In most of the problems with the current, because current has to have a direction, right? Which should flow. And most of the problem I'll be asking based on the wires. Okay, the current usually in practical purpose we pass through this one, right? But I can also pass the current through the sheets, right? So how you approximate that, or in your, or let's look in a different point of view. Once we deal with the Gauss's law and all those the other steps, we were talking about creating a uniform electric field, right? How do we create a uniform electric field? We just keep two places. One is plus Q and another is minus Q, right? And this field will be sigma over 2 epsilon. This also have sigma over 2 epsilon, and this side will be cancelled out, right? This side will be, right? So this will be add up. So you will have get 2, sorry, in this region for the case of electric field, right? So there is way to create a uniform electric field. You just take two infinitely long plane. Ideally, it should be finite, but we assume that the distance between them are so close that the length or the size of this sheet is so much like so. That's what we did. But how we create a uniform magnetic field? You cannot create a uniform magnetic field by using a single wire, because with a single wire, your field always will be curling like this, right? So if you want to create a uniform magnetic field, you take several wires, right? So how you look the magnetic field with the several wires? Let's assume that you take infinitely long wires, which is basically sheets, right? And you create the magnetic field. This is carrying I current, all of them, and you just say this is infinitely long sheets in all direction, right? Now you find the magnetic field produced by this. We look the magnetic field for infinitely long sheet. So we use the same idea of the wires where we were looking at the cross sections, right? If you look at if you take, for example, this is infinitely long sheet, right? And you have the wires like several of these wires, so the sheets, right? And if you look from this side, the cross section from this side, it will be looking like the wires will be coming out, right? Right? So it's simple as that. Okay? So if the wires are coming out, several of the wires are coming out, right? And you have the direction this way. Now, if you look at the magnetic field for each wire, so how the magnetic field looks like for a single wire, you have a wire, right? And your magnetic field will be, if this direction you have current this way, you have field like this, right? If you have a second wire, what happens? You have the another field current like this, right? And you have a third wire, you will have another field like this, right? So what we do basically to create a uniform magnetic field, we squeeze the wires and keep very close. That's how the sheets are, right? Which means you have this wire here and you have another wire here, another wire here, another wire here, another wire here, like this. And your magnetic field just go like this, right? With this direction. Understood? So you keep the wires so close so that this field will be added and you just get a field like this. And if you are going much closer in such a way that you just go very closer, you will get a field added to all of this. This is how you have to see the sheets. And how you find the magnetic field, the total magnetic field created by such kind of a sheet. See, this is not infinitely long sheet. You use Armenian loop, right? So you take this kind of for draw wires in a separate, and this is going infinity in this direction, infinity in this direction, and infinity in this direction, infinity in this direction, right? You have infinitely long sheet. So infinity in this direction, infinity. So it's a big sheet. And I'm only looking at the cross section this side, so I just see this. Okay? Now I can have the field going this direction from here. Okay? And I can have, because this wire will have, the field will be like this, right? So I can have field lines going like this. And when I look at this direction, this field will be, right? So you have wires coming this way, right? So if this field is B, this field will be B in this direction, right? So this will be having this direction. You got it? Because if I take a single wire, the field will be B here in this direction.
Boy, he's drawing at this point, so I can't.
Yeah, let's do quotes.
Huh?
I
Are
think
you drawing
you're-
also?
You explain it, yeah.
I'm saying you're drawing also.
Yeah,
Okay, now he's doing the question.
yeah,
And
don't.
here, loop. You should have a loop. Right? So you just draw as first loop, and then you just put the direction of the field, and just name it as first part, second part, third part. Like in most of them, we just split the closed surface integrated into a cylinder, the side, top, and bottom, right?
Yeah, we named each part, so part 1, part
In the case of magnetic field, when you have a square loop,
Yeah.
right? And how you solve this? So this will be B dot dl, right? Close integrated mu 0 I E. Right? So the crucial part of this one,
E dot
whenever you're defining
EN is equal to
ambiguous loop,
mu 0 I IN.
when we were solving these kind of cylindrical problems and all these things, we defined the radius, right? Remember, when we have the infinity long wire at a distance of r, we always define the radius. But when you have a square ambiguous loop, you just make the length, okay? And you just have to check number of wires per unit length, L, okay? And you can call them as N. There are n number of wires are coming per unit length. So what will be the total IN?
N I N. N.
Whatever the number of
be
wires
N.
coming?
The number.
Five, right?
I'll write the
So this will
number.
be number of
Yeah,
wires
yeah.
coming in that particular length should be that. So you have to have that particular length. Okay? And then this one you can split into 4 parts. Open integral V dot dl for the first part, plus open integral V dot
First
dl
one.
for the second part, plus third part, plus fourth part should be equal to mu 0 n I into whatever that angular length. And what is the first part? The magnetic field and the length are parallel, right? So you have this one, and the second one perpendicular, right? This is the direction of the length, and this is the direction of the field. So this will be 0. The third one, you have parallel, right? It's 180 degree. And then this one will also 0. So you have 2 times of B dot dl because they are having the same length, right? This L and this L are same. Should be equal to mu 0 n I into L. And what is the dl here? It's an open integral of only this side, right? You're not talking about the closed integral of L. Just this side. So that will be,
He named it 2 because we only have 2, yeah?
right? So
Yeah,
this will be
And why did the
B
2 and 3 cancel?
mu 0.
2 and 3.
You said they became 0.
Yeah, because it is 90 degree.
Hmm?
Cos 90 is 0.
What did you say?
Cos 90 is 0, that's why.
Oh yeah, because 2 is like y-axis and 3 is like x-axis, yeah? And
Yes.
they like create a 90 degree, right?
Yes, yes.
So that means it's 0? Do you understand what I mean?
Cos 90 is equal to 0, right? So the whole thing will become 0.
Yeah, cosine 90. It's
Yeah.
like Gauss's law.
Yeah, exactly.
Okay, and L can be cancelled out, right? So I will get a magnetic field B should be equal to mu 0 n I over 2.
2 pi r.
Right.
L.
Oh, sorry.
What?
This taking should be that, right?
What the fuck?
Because this is perpendicular and this is
Oh, because they're perpendicular, that's why he cancelled.
positive.
Yeah, that's what I just said.
Yeah.
Why did he make it?
Cross product is yeah, this, yeah. Dot product, just assume that 2 vectors. This is not part of our vector, but dot product we are just checking how you have one vector and another vector, how they are projected together. Right? Where they are equal, then this one will be nice. Now, see, you have seen here, when I have a shield, it depends on the uniformity of the shield, right? I create magnetic field with some beginning, right? So this is not a perfect solution to have a uniform magnetic field. People thought about this, how to create a uniform magnetic field using a shield, and they come up with an idea. You take a shield, right? And you look at the magnetic field, and if it is, you have any misuniformity in this number of elements you are taking, you will have that much disuniformity in the magnetic field. So what people did, they take a shield and they fold it. Okay?
They take a shield, they
Now it
fold it
doesn't
and
matter whether your
put like a
wires
wire
are-
around it.
Having
Yeah.
any misuniformity, if you take a shield.
Okay,
not
now he
a
will
shield,
do
you take a,
solenoid.
not magnetic. And you take a single wire, right? And you just wrap them. Instead of having a conducting shield, you take a normal wire, right? And you just wrap them in any direction. It doesn't matter the direction. Like this, right? And you can get some magnetic field inside of this one, right? Just let me draw it. And these things are called solenoid. So you have a cylindrical shape of an element, right? You have the wires going this way and coming out, and then going this way, coming out, the other side, this way, right? So you are passing some current in one direction, and the current is coming, right? And these kind of things can produce a uniform magnetic field inside. We will check how it is producing uniform magnetic field quickly inside the field. So you have this kind of stuff. Okay? And now we will check how the magnetic field inside of this kind of
You stop the video? Or?
So-called solenoid, and how it is useful for certain project like nuclear fusion. We'll first.
Bro, this is how you study, yeah?
What?
This is how you study?
Sorry?
I'm saying this is how you study?
Through the video?
No, like you say you have exam. What we did, me and you, this is the same way you study. You would study.
Yeah. But like, sometimes I don't study, like, like I study last minute.
Mm-hmm.
Yeah.
Okay.
I'm too lazy.
Just asking it. Okay, no problem.
Alright.
Then we'll just discuss the importance of this. So, remember, the electric field we created to deflect the charge, right? The uniform electric field we created between two sheets. If you pass a charge, you have the sheets and you have the field inside, right? And you have a charge particle moving with some velocity, right? Depending upon the field direction, it will have a force, right? And then it will bend, right? Why are we creating this polymer? Like we want the uniform magnetic field. Mostly, if you keep a charge particle in the uniform magnetic field, what does it do? For example, you have a charge particle going, or you have throwing a inside the same field. So you have a charge particle moving with some velocity, right? So velocity will be in this direction and your magnetic field in this direction. Which direction is your force will be? First vector. And second vector. So your force will be this way, right? So you have, for example, this is your charge particle point. The charge particle will just circulate with that force. So if you have a uniform magnetic field, you can basically store or accelerate the charge particle in the same point. That's the idea people wanted to have a uniform magnetic field. Okay? So now, we create it by using this solenoid. So we have a solenoid, a non-conducting cylinder, okay? And then we just have the wires. Your textbook, you will only see this kind of wires, okay? You will see this. You can have several. So the other side is just find it the other side of this cylinder. Now you have the current passing through this, right? How you find the magnetic field inside? So you have some field. So if your current is in this direction, your field will be which direction? This one. Okay? So your field will be this one. And in the case of electric field, the electric field lines start from the positive charge and end at the negative charge, right? But the magnetic field behaves very strangely because you don't have a magnetic monopole. It means you cannot have a single north pole magnet. As I mentioned in the first class, magnet, if you break a magnet, which is already having a north and south pole, you will get a smaller magnet with north and south pole, right? So the field lines, if it is going this way, it will not end to any other point. You just loop around. Okay, but if you check the charge, the electric field, it just starts from this and ends here. Right? So we have this, right? It never go this going back. So this will be depending upon your distance from this one. So it will be having a loop around. Okay, so the field outside is going this way, and inside is this. Okay. Now, how you find the inside magnetic field for this kind of? So whenever you have a wire winded like this, you always check the cross section. So the cross section will be of this one. Through this one. I take we have 2 minutes. I'll finish it, okay? So if you take this region, okay, so you cut it and you will see that the wires will be coming out like this. Okay? And you take a long solenoid, infinitely long solenoid, and then you can use, maybe you continue from here for the next class, but you can use the ambient loop this. So you just number 1, 2, and 3, and sorry, 2, 3, and 4, and you have the field in this direction, right? And outside you have field inside. And find the field. What is the, this means that you just, if you cut this one, you will have one side like this, you have another side also like this. Okay? Just, I don't know how to slice a cylinder, make a slice of cylinder. That's it for today, and we will continue this chapter. We only have one more topic. We'll do a couple of rounds from this if we have time, and then we'll do the toroid. Then we'll finish this up. In the last class, there are imperfections in the magnetic field depending upon.
Oh, this recording is a bit bad, huh?
People found
So you have to like listen to him, huh?
Instead of having
Yeah?
This recording is a bit bad, huh? Like when he goes to the left side of the board, it's a bit like hard to see.
Yeah. Pay
So
attention.
just pay it like by hearing it.
Yeah, yeah. Right.
They just make this close, right? And this wire over it. So ideally, when you look at that, this is insulated wire, insulated material. So ideally, when you look at that winding makes a circular loop, right? So how the magnetic field look like when you have something like that? Now you are winding the wires coming down, again the other side. Right? Now, how the magnetic field will play? So definitely you have the current this way, right? So when you have current in this axis, the magnetic field will be around that wire. Will be like this, right? So when you look at the magnetic field, you have field. Also, you have wire here, right? So this also makes the magnetic field. So you have a uniform field inside. Right? How do you find the magnetic field inside and outside of the circle? And what about the outside of the circle? This is inside, right? So if you have a magnetic field inside, it should come. And it should get
Bro, did you
Unlike the
wait? Stop,
electric
bro.
field, because it can be positive
Did you write? Did you draw until the last one when he wrote the cross section? If you
Yeah, I
did,
did.
if you did skip until like skip to 5 minutes, because he's just repeating the same thing, I think. Skip to 5 minutes exactly where he starts writing down the equation. See here? Yeah. Huh?
And what is the
What?
No, just see he started writing it down.
Yeah.
Yeah.
So this is very blurry though.
It's the same. B dot dl m mu 0 I m.
Yeah, okay.
we don't use it. You can split them into four sides, right? So total integral we will use plus we will use four sides. Actually, a function of the sides. Let's say
See he wrote all four. One,
Yeah.
two,
if you look at
three.
this
Stop here.
it should
We'll
be
just
equal
write
to
it
zero.
down.
What is the I?
Same thing. So first we write what? The first one, BDL. Is it BDL or?
Yeah. Ideal.
Oh, it's still integration. Okay. Integration dot BDL 1
Mm-hmm.
plus plus 1, 2, 3. 2, 3, 4. Okay. يلا كده. You don't need to write it exactly, by the way.
Yeah, okay. What the fuck? Wait.
Hmm?
I'll play it, yeah?
Yeah, play.
Right? And if you look at this one, this should be equal to V0. What is the I? It's 7.
Oh, number, yeah. Same as last time, remember?
Because there are several wires. Now, what about the first side? This is the direction, right?
So second and fourth cancel.
The
Yeah.
second side is making 90 degrees, right? The V element is something more.
Okay, so you write again 2
Same.
2 integration b dot dl, yeah, is equal to number.
Solenoid. You see, you have more or less constant magnetic field inside. Okay? So inside magnetic field is almost a constant field, and it is more intense than the outside. Right? The outside, when you look at these fields are called fluid fields, which means you go away from this one, it will be decreasing so much. So ideally, even if you look at the ambient loop on outside, you see if you have the current is coming this direction, so your magnetic field goes. Your magnetic field goes this way, right? And this magnetic field goes. This will go this way like this. This will go like this. So if you look at here, the field on this region, or the whatever it is created in this region, they will almost cancel out. So for all ideal purposes, even though there is a magnetic field here, for all ideal cases, we take B outside approximately zero. It will be never zero. That's why we call them as fringe field. Okay? So this region, the B is considered to be approximately. So we only have the first region, it would be U0. Now let's see what are the current coming in the inside view. So you have, for example, you have length of L is the length of this total solenoid. You assume that you have n numbers of wires are coming out. So this, whatever the numbers, assume n numbers of wires are there. So ideally you should have the IN should be whatever the number of wires and whatever the L, the current, right? So IN should be, so this, what is the DL when in this I forgot to mention that. Whenever you take a look, you have defined the length of the annual loop, either small l or the capital L, whatever you define. So this will be mu0 n into I. But particularly for solenoid, you must have seen a different equation, right? So solenoid always talk about, unlike the sheet or any other predefined numbers of wires, solenoid always you can change the number of wires or number of wires, right? And we will talk the n number of wires in terms of how many numbers of wires you can fit in particular. If you and equal to number density. Number density. And what is number density? If you number of wires, total, right? So this n you can write number density to. So this will be mu0 n L in I. So we will have magnetic field mu0 n. Okay. This is the reason for the solenoid. We always talk about the number density of the wires or the density of the wire, how you fold them around to cellular loop. And if you have more compact and more dense wires, your field will be stronger inside, right? So the magnetic field and the length element, right?
Yeah, and the weight.
Which one? So I'm talking about this. When you have this wire, for example, this is my wire, the current is coming out, right? So if you look at around the magnetic field, the current is coming this way. So your magnetic field will be this direction, right? So this one will be this direction.
So magnetic field will cancel out.
Yeah. But it won't cancel out entirely. You still have magnetic field, of course. But it partially cancels out. And also, if you look at compared to the inside one, the outside magnetic field anyway you have only from this section. But inside it is combined from this section and this section, right? And also this is kind of less dense magnetic field compared to the inside one. And if you ideally look, the current will be sorry, the current is coming this direction, and the magnetic field for this one will be this direction, and for this one it will be the same direction. But if you look at this side, it will be the opposite. It goes in just meters. Now, so this is not a, I mean, even though you have this solenoid, the overall idea is to create a uniform magnetic field, right? Yeah. So you can define this as model. This is the ambient loop test. Whatever the length you want to use for ambient loop, you can take the whole. Now, people wanted to use this for some purposes, but the problem with the solenoid is good, but that's the problem with solenoid. You can create the uniform magnetic field by using the solenoid, but ideally you cannot use them for any. I mean, you can use for some purposes, but the whole idea is to use to have some purpose, like for example, if you have two plates and you apply some electric field, you can reflect the charge particles, right? So people are thinking we can do something like that with the magnet, and they found if you have a uniform magnetic field, you can store the magnetic field in a circular, right? But when you put the charge particles inside a uniform magnetic field like this, since your winding cannot be perfectly circular, right? You will have always have to have an angle. So you even when you create a uniform magnetic field, when the charge particle travels, they will just they will come back to the same position, right? So they will eventually lose. And then people use, there are several other techniques to store the particles. So they keep some other kind of permanent magnet here, right? And they apply some magnetic field depending upon what you want, and they create some field around here, and this particle will be going back, and particle will come back, and they will store it. But this is not effective. Since you have a fringe field so much here, eventually the particle, even though you can store, they will just lose it, right? And so people came up with a solution. Instead of having a solenoid, why don't you make something like, so if you want to store the particles, you have to keep the solenoid, so you have uniform magnetic field inside, and if you want to trap or store the particles inside, you keep another magnet here and here, and then they will be trapped, right? So instead of that, remove this magnet, you just make a loop, right? So that everywhere it is, since it is a loop, the magnet will be uniform all over, right? And you store the particle in this circular, and they call them this kind of geometry, of course, right? So now we'll talk about something called toroid. Toroid is not only useful for creating or storing the charge particle or trapping the charge particle. There are other purposes of the toroid also. You must have learned about the toroidal transformers, right? You keep a magnet and you wind some wires. You will learn if you have time to learn about the nature that will be using this toroid. So what is the toroid? Basically, you take a solenoid, right? you. You take a solder and you pour it, right? And then connect it. So ideally you have the wires are connected, so it will be like this. So we wind the wires, so the current will be going like this. And this is really useful if you want to create a core charge particle, particularly for the nuclear fusion. So the core charge particle. So what is the magnetic field of the in terms of Tesla? How much is the 10 to minus 4 Tesla? So something like millitesla, right? This is the Earth magnetic field. If you want to create a plasma which can create which can induce the nuclear fusion, you know how much magnetic field you need? Something like more than this. So far we could create only in the laboratory, specifically in some project called ITR, International, they have a nuclear fusion experiment going in France. So ITR project, so they have created a magnetic rod which can sustain something like 100 Tesla. But the problem is that when you create a magnetic field, you have to apply a huge current, right? When you're having a huge current, what is the cycle flow? And whatever the torque is doing. So you need to have a superconducting lobes, right? And so far we have not created superconducting wires of these many magnitude in a laboratory. Even though we create something like very 4 Kelvin, 5 Kelvin, we are talking about something like minus 270 degree. So, and they could create some of these things, and the problem with this kind of fluoride is that even if you have this kind of charge particle, for example, for fusion, we typically used to have the hydrogen. Two hydrogen come together and fuse them, and make the, and whatever the mass difference will be converted. Anyway, that's what fusion creates, right? And how much time they could sustain this fusion reaction so far? They even could not produce this fusion within for a second. It would survive that much, because when you have that whole particle plasma, and you have the fields going like this, in this toroid, right? Even though you have the toroid with very dense number of wires, that will be a little bit different production. And this whole particle can go and be from the parts of toroid. And the toroid, whatever the idea project they make, they mostly the walls and the almost one part of the toroid they make some special kind of ceramic which is coming from the mica. We use mica for the now we shield the rockets from when we send to outer space. We basically place the shells whatever we are finding on the beaches. This is not the exact shells, but there are they make some other kind of ceramics mixing with that. And these are kind of tiles. And you can see when if you look at the rocket launch like SpaceX big rockets, right? Sometimes you will see some of the parts will be falling from the top of the rocket. These are mostly the tiles. We cannot fix this one so into that rocket when these things are fired. These are fired with something very huge temperature. So even though they are surviving this kind of temperature, but you cannot stick them. So this is one of the use for hardware cover. So you will not have this kind of questions, but you will have questions like find the magnetic field inside. Find there are 10 kinds of wires. The wire is sliding. Magnetic field inside. So you have a toroid. Let me try to blow this one. You have a toroid, something like this. And this is something like this. Right? Let's assume that for simplicity, let's assume that this square on the board. This is flat toroid side on. Okay? And I have the wires on like wires on. I don't know if the drones are very bad. I'm pretty sure it's bad. I don't know how much bad it is. So you have some wires are all there and you can direct this direction. You can have the other direction too. This is the forward, so it's symmetric. Doesn't matter which direction you pass it. And this will be going reverse. Not bad. to make a 3D one, or 3D thing. Should I state my information? Now, this is something like this. You have some coil. Now you have the wires are mounted like this, okay, and the currents are going into some kind of loop, right? Now find the magnetic field inside it. How do you find the magnetic field inside? So you make a cut of this one. What's this? This one, cut this. Inside this, I mean this side, okay? Don't get confused. What about this side? Yeah, in the middle. Yeah. Like it is a torus, and you have a torus, right? Like this, and you take this, like a birthday cake, and you cut the cake from the middle, then you take it, and you decide that okay, I'll slice the cake after first cut to the middle. Right? Then inside you have something. Right? So if you look at the inside, you will be finding this way. So your field will be looking like. Yeah. What is this? Right? It's a. When you look at this, the current will be going inside, right? Will be working. Outside will be. It depends which direction you look. This side of you. If you look from the other side, it will be opposite.
No, but yeah, the outside is going up like this way.
Yeah, you're looking like this from the top. So the wires are coming up, right?
Yeah.
From the side and going in.
Yeah, from up, they're going up to the bottom.
It depends if you look from the below side. If you look from the below side, it will be quite opposite. I'm looking from the top. Okay? So how I solve this? You get this, when you cut it, it will be looking like this. So you just draw an ambient loop. Right? So you assume that this is having something like R1, this one is R2, right? The ambient loop is having, just you can define the R or whatever. So what is the period here? U0? I, in, right? What is the I in here? Over wire, n numbers of wire, carrying the current I. Right? Here you are not dividing the numbers, or you don't need to know how many numbers are there. You can, when you talk about this one, whatever the wires you are binding, right, you will have all of them going in, right, in other direction. So your mu0 I will be u0 n, right, and this will be, what is the loop dl of this one? The length of the loop. You have, let's say this
2
R.
pi.
2 pi.
You understand what's going on?
So the magnetic field will be mu0.
You understand what's going on?
Well, this part is just you just put the same equation, min, and then
Yeah.
you turn the in into what? Into ni, yeah.
Yeah.
And you turn that the dl. I mean you'll take the b outside. It will become absolute b.
Hmm?
After you take absolute b, it will be integration dl. And what's the integration of dl? L. And what's the L? The area. The area of what? The circle. What's the area of the circle? 2 pi r. And then
Yeah.
we'll take the 2 pi r down, and that's it, I think.
Dumb.
And
You
then
know it.
r1 less than r less than r2.
Alright, good. You know it. Alright, fine.
Huh?
Yeah, you're right. It's good.
You sure?
Okay, I'll just stop playing.
This topic is kind of, I mean, once you understood the topic, it is easy. Yeah.
R1 or R2?
R1 and R2 are the dimension of this one. This is radius, inner radius, many of our don't, as I said,
Yeah.
there's inner radius. This is called R1, and the outer radius is R2,
Yeah.
right? So, the ambient loop is the radius of R.
Okay.
I define that R.
Ah.
Right? The limit of the ambient loop can be from R1 to R2. Right? If I ask you what is the magnetic field on the surface or just below the surface, you should replace it. So this one will be E will be
The one you take for the outside will be outside of R2, right?
R2 is the outside radius of the, when you have a donut, you can have
No, I know, but it's only inside the door.
it's only inside. And now, you can write, but you don't want to write. I mean, but see, when you have any numbers of, see, the reason here we have written, you can have a different length, you can consider a small number here in this ambient loop, right? But when you're talking about the ambient loop here, whatever the numbers of wires you take, you cover all of them in the ambient loop. That's what you're doing. If you want to write, you can just write the numbers. Just write the, instead of n, you can write the whatever the number into whatever the. So that will be the length. Right? Now, this is okay. This is how you can use words. But in our normal life, use same idea, something else. You all heard about the coaxial cables, the cable TV cables in your home, right? There is something unusual about those cables, right? So let's do this. This is the last example for this. chapter. And you can have several simple problems in the back of the chapter. Just practice with it. And if you find anything difficult, just take it. So coaxial cable, if you look at the coaxial cable, you see that there's a pin coming in the middle, right? The cable to the cable. And then that carries some current, right? So when you connect the coaxial cable, in olden days when we used to have this issue with the cables, we just first thing we do that we check the connection, right? The reason for that, whatever this current coming here, will be connected this first on the other side. This current will be going up, right? And find the magnetic field. So coaxial means that you have, for example, this is your the wire, this wire, right? And this is the other. There will be inside shielding, and on top of that there will be another cylindrical wire, right? So they both are sharing same axis. That's a coaxial. Okay. This will be used if you go to any research lab. You can find hundreds of these scripts. In our lab, we have a lot of cables. We use for all the electrical connections and for all the electronics processing functions. We use coaxial. There is a particular reason for that. When you are doing these very high precision measurement by using like something like what we do here, probing an atom or molecule with femtosecond precision, if you use the normal wire, they carry signals as currents, right? They create some magnetic field around it. And if you have another signal going some other direction, it's related to some other interface. So this will interfere with that. And you either you're talking about very small signal, something like 0.05 volts of current, and you will get a lot of noise on top. So when you look at this data from, especially from Mars mission and all these things, you must see that whenever they are talking about they found life or signals of the molecules which then possibly create life, they show some spectrum, and you will see a lot of crystals. They will be showing something like this. They say this is a signal. And there are different ways to isolate the signal. They know. But the problem is that, unlike PET, you cannot exactly demagnify whatever the wires, whatever you're using. So whenever you have a signal, you can have interference with signals from the whatever you are getting. So let's see inside, outside. And in olden days, all the I think still also there are some countries they use the coaxial cable for the Wi-Fi, and also the cable television. And in olden days when we didn't have the cable TV, what we do, we just take a pin and just hear the cable, we connect the pin, and we connect the wire, and we can just get the signal out. Because whatever the signal carrying, it is a current, right? So produce the magnetic field, and that magnetic field releases current from whatever the wire we connect, and we can get all the channels from it. So people use different things, but nowadays I don't think this is very common use. They have the internet, chips from the dish TV or cable TV to something for Netflix and other Amazon brands. So let's come to our topic. So you have a problem like this, to find the magnetic field inside and outside. So immediately you can say that, what about the outside magnetic field? So when you draw a loop, ambient loop, there is some current coming in, right? One current is in this direction, right? And another current is the other direction. So you get zero. So mu0 I is 0 from the outside, right? So and what is B inside?
B dot dl is equal to mu 0 I.
I'm not going to the details. So you just write mu dl.
Take B to the other side. Then dl will become 2 pi r and then you just put the 2 pi r down.
Yeah.
And that's it. And then he just, after this, he just explains like random stuff.
So it's enough, yeah?
Huh?
So you want to stop here?
Just like put it at 2 times speed and like look quickly. Yeah.
Okay.
I mean, just hold it. No need to.
Fine.
Shit.
And then I'll be asking questions to find the magnetic inside and outside. So you information. I recommend go to the textbook and see the problems in the backside of the textbook. You don't need to solve all of them. You read the question. Some of the questions, some of the questions are from there. When you read the questions, you will understand. You don't need to read into the maths. It's very easy to understand. But some of the problems you have to do. You have to understand geometry of the flow. So once you understand, for example, if you know the right side of the one side is the incoming current, other side is the outgoing, then definitely you know the load current is zero. When you look from the outside of the ambient loop, then you can say that's zero. And inside you just decide whether it is for the ambient loop. And practically, when you use this one, you use something with the resistor, right? And you have to do something with the resistor. There are some problems you just forgot to use some potential for that. Yeah, in between you have a data. These, that's what I said. There is a shielding loop, right? So basically, what they do, you have this wire, right? And in between, you have some direct medium, right? Why do you direct medium? They don't pass current, right? It's a direct medium. And then you have a shielding. So what is that shielding? Shielding covers part of the magnetic produces inside. So you have a separate shielding. That's what inside. And there are different styles of cables, typically for signal processing of in laboratory. I don't need to talk about it. The feature for signal, right? 5 volt, 0 to 5 volt, like pulse going. This is the capacitor. This is a 0, this is 5 volt, right? These are called feature buses, right? And this feature buses you see something called BNC cable. And this doesn't require, to have a very solid or very expensive magnetic field. So this is for example, you want something called high voltage. So for example, you want to carry a 1000 volt without any voltage. So you use something called capacity cables. And particularly for us, it's something nuclear, something like that. System we use something called nuclear. So this is 0 and this is 1. So these are the real things, and there are things when you talk about these kind of things. So there are, you can see different varieties of lights, different shape of the lights, different types of the lights, but they all have coming together question. So the current one is the cheapest one. Yeah. So that's what I said. It depends on the purpose of that. They choose the direct application, right? So whenever you are doing these kind of material, you want, right? However, you cannot make it, you cannot make it new. So these are, compared to this one, these are 5 times expensive. If you are talking about this, maybe you have to pay $200. For this one, you can get it $200. So depending upon the material inside, you can have magnetic field or not. No, they are not increasing the voltage. Here we are not talking about the voltage. The direct material is just shielding whatever the magnet. It's not actually the direct material shielding. It is just making isolation between the current of the whatever it is the current flowing to the inside of wire, the small wire.
But stop it, stop.
But what I can say, even though you have insulation, right?
Boss.
You keep a wire.
Broski,
Yeah.
check the comment.
Comment?
Yeah.
What? Who wrote this?
It's me, same channel.
Oh my god.
Okay,
Nice
that's it.
timing. Nice timing.
Okay, it's been 1 hour and 41 minutes. We finished
Yeah.
chapter 29. Finished chapter 37 and 28.
Yeah.
Okay, now we do questions.
Yeah, we'll do questions. Do you know where the questions are?
I mean the same as we did. Didn't you write them? Didn't you write them, I say?
Yeah, but like, you wanna do the questions which he did in the class or like
Yeah,
the
the one that he did. No, textbook, bro, it's so bad. Like, I can't understand anything with the textbook. What
Okay.
Najib gives, I think, is better.
Alright. Do you have the textbook questions though?
No, do you?
No, I don't. It's fine. It's okay, we'll just do this. And also look in the group. There are some people like, posting a lot of questions, we'll do that.
Bro, they do extra stuff, bro. These guys are like you, bro. Two nerds.
What do you mean like me? I don't know, it's just
Can you take this? As a comment?
what? Oh shit.
What? Good. Like, okay, coaxial cable, this is like easy. And this is the last one. Either antennas, wires, area, wander around. Bro, do you want to take a break or no?
Yeah, I wanna
Or
take a
you want-
break.
Or you want to finish everything? Like, do
No, I wanna take a break.
Okay, so what time do you want to come back?
What time do you wanna come back?
What about? I want to know about you. What's your opinion?
I mean,
Huh?
like I think like 6 o'clock maybe.
After prayer, you mean? If I go prayer.
Yeah.
Sure.
You're okay with that?
Yeah. And then how long you want us to stay?
Questions is not gonna take that long. Like
Hmm?
maximum 1 hour, yeah.
Bro, we don't know.
Yeah. It's fine, we'll see.
I think max, like, I'll just say minimum is 1 hour and 20 or 30 minutes.
Yeah.
And maximum is like 2 hours and almost 2 hours and a half. No, maximum like 3 hours. I don't think
Yeah.
it'll take that long, yani. We'll just do questions and learn how to solve them, you know. That's
Yeah,
what
okay,
matters.
cool, perfect.
Okay, what I have a problem only in what in this one. Remember the very long one,
Yeah.
which was it? This question, the
Yeah, I
infinity
know, I
long
know.
wire, yeah.
Yeah.
That I have a problem on, yeah. And then
Okay, fine, we'll do
28
that.
we'll do a couple of questions, and 27 couple of questions. Yeah, we'll just do what he just showed us. Okay, bro.
Alright, fine, I'll join back in like
I'm gonna go like relax a bit, sit
Fine,
on the bed,
fine.
and just get ready for prayer.
yeah.
Like I'll be
Nice.
like 6, 5, 10.
Yeah, alright, fine. See you, bye.
You'll close the stay on Google or you want?
It's fine, we'll leave it. I'll join back later.
Sure, come on. You don't lose anything. You want to charge your phone, yeah?
What?
You're on your phone?
Yeah. No, I'm on my laptop.
Oh, okay. Yeah, no
What?
problem. Okay. I will keep the recording on.
Okay, you keep it on. I'll just join back then.
يلا.
Yeah, it's
Hello.